Is the PPT visible? Is the Keel compiler visible?
Yes, sir. The compiler is.
Hello?
Yes, sir.
Yeah. I just posted a message. Please try this program before we start. Another 5 minutes, we'll let them join. Before that, you can just try this program. So do certain modification, check the working of the flags and the meaning of the flags by that time. Am I audible?
Yes, sir.
Yeah. So hope you have done that program, whatever I displayed there. We'll continue from there for another the next 30 to 40 minutes. I'll explain what are the programs, how to do it and everything. So then I'll give the first lab program, 1 or 2. So which the exam programs. So then you can work on those programs and show me the result. So 1 or 2 tasks which is not there in the program, I'll also tell you should be able to think how to do it. So listen to me carefully. So next 30 to 40 minutes. And hope that everyone, you can keep trying with me also. There's nothing wrong. You can parallelly keep trying with me. So when I explain certain instruction format, you can try that. So I expect everyone has got the Kyle environment ID is available and it's working. So if not, so don't tell me that I'll be showing in the evening and everything today onwards, because these programs does not require much of the time. There is no much interventions is required from your side. You have to search and everything like that. Earlier programs like things speak. So you can just do the program within another 1 hour and you can show me. So 30 to 40 minutes. It's a 1 hour till 3 o'clock. I'll demonstrate. Then another 1 hour is good enough for you to do the programs and show me. So make sure that you have the system with you and keep trying that. Is it okay? Yes or no?
Yes, sir.
Yeah, we'll go like that. Okay, I'll stop the execution. So I'll stop the execution. So I will start with the very fundamentals. So as we already know that, so we should have, this is the format of your program. So whatever I have written there, if I remove this also, so it is called as the empty structure for assembly program. So now no instructions are there in this program. What you have in instructions, I have removed. Now whatever you see is only the instructions to assembler. So whenever you write a program, there are two concepts are there. One is called as instruction to program, instruction to assembler. Other is called as instructions to your core, ARM core, or the ARM microcontroller. So based on that, all the statements, whatever you write in assembly language program, will be classified into two types. So they will be called as, so number one, they are called as assembler directives. Assembler directives. So these are nothing but what? Instructions to assembler. So what is the meaning of instruction to assembler? I mean, this is the end of my program. So this is where my program code starts area. This is where in the code, the first instruction to be executed. So like this, these are the different directives we'll be using in the program. So these are not having binary equivalents, in the sense, when I convert this into a program, you will not find even a 1 byte of memory occupation. So if I go to this program, whatever the example ASM, if I compile this program, I'm just compiling the exam.this program. So it says that, so does not point to instruction. So one instruction should be there. In the sense, I am not able to compile itself because there's no instructions are there. So let's put one instruction. So move R0 comma hash 10. So now in this, one instruction is there and 3 instructions are there for assembler. So 3 instructions are for assembler, 1 instruction for ARM microcontroller or ARM core. So continue from here. I'll just finish that whatever I have written there. So one is assembler directives, other is nothing but so ARM instructions. ARM instructions. Okay, these are the 2 contents of any ALP program. So ALP program comprises of these 2 things. What are the examples for ARM instruction? So you know that move, add, these are all the type of instructions to the ARM microcontroller or compiler. So these instructions will have an equivalent binary code which is stored in the memory. These instructions to the assembler do not have binary equivalents, so there is no representation in the memory. So what I can say, this I can write that no equivalents are will be there, and no memory is required. No memory is required. There are only instruction to assembler, how you to assemble. Whereas these are binary equivalents are there, that is hex code will be generated. Equivalents are generated. So these binary equivalents are decided by the ARM core manufacturers. They said add means this is a code 1010 like that generated, and memory is required. That is, you occupy certain bytes. So we have found the definition of assembler directives, and we have also found the directions, in the definition for ARM instructions. So these are basically instructions to the ARM core or ARM microcontroller. We understood. Our assembler directives are instruction to assembler. Example, this is the meaning. ARM instructions, instruction to the ARM core or microcontroller. These are the examples. This is the meaning it carries. Now come back to the program here. Now I've added 1 instructions. We will see that you may ask me, sir, how do you say this is an instruction? How do you say this is not an instruction? So to prove you, I have included instructions and directives, and I compile the program. Now there is no errors there. Now I'll start running the program. So when I start running the program, I want to see what is the equivalent of every. Whenever you write a program in a high-level language, starting from assembly language, what are the high-level languages? Where we represent them using English letters, using mnemonics. Where we use a word called move, add, we call it the mnemonics, shorthand notations of the meaning of the instruction, which has been generally given by the designer of the ARM core. So if you move little above this, that is a more abstraction, if you look at it, then you have high-level languages like C, C++, Java, and other things will be there. So in the low-level languages, we have assembly language. When you move to the high-level languages, you have other languages like C, C++, Java is there. So ultimately, these languages, low-level languages and high-level languages, convert their instructions into what is called binary format, 1s and 0s. Why? Because ultimately the program has to be stored in a memory. What is a memory? Memory is a set of bytes. As I was discussing in the last class also, in the last lab, memory is what? Set of addresses. Every address represents one byte, ones and zeros. So memory can store only ones and zeros. And this ones and zeros will be fetched by your ARM core to execute the instructions one by one. That is fetched by your CPU. So naturally, whatever the language you use to develop your program, whether assembly language or next high-level language, ultimately I have to store ones and zeros in the memory and then start my microcontroller. So the microcontroller can fetch these instructions one by one and execute it. So when I say that whenever I convert the instruction into binary format, that means that there is a representation for every instruction. If there is no representation in the memory, it is not called an instruction. So I want to check now to show you now only instructions will have the memory equivalent, and non-instruction like directives will not have a memory representation because it was of use till you convert things into machine language. After that, it is of no use. For example, area, reset, quote, entry, end are of use only for the time being until you assemble your program. The moment you assemble your program, assembler will learn some meaning, will understand something from these type of statements and use that meaning, then convert every instruction to machine language called ones and zeros, and then give a file which is nothing but ones and zeros file. So in the file finally which is generated by an assembler, do have the binary equivalent of area reset code? No, it was required only till the conversion is over. After the conversion was, there is no meaning is there. So that means that assembler directives have a significance only at the time of writing the program and during conversion. After the conversion, it loses significance. So adding that, I'll stop for a moment. Okay, I'll add one more line statement here. So what is the thing we have to understand is, so this is the first concept, let's say. This is the second concept. So what is the job of assembler? Assembler converts the ALP program to machine language, that is ones and zeros, which so during this conversion, assembler directives help us during this conversion. Assembler directives help the assembler for proper conversion. Okay. So after the conversion, there is no machine language representation of the directives. So going back to the program, so I will just show you this. So now I'm just going to the few more windows which we have not discussed in the last lab. So this is your program. So I will keep my cursor here. Okay. Okay. So now look at this instruction, disassembly. So here 0x0 is a first instruction. Move is stored there. Move R0, this one. So after that, I do not have any other instruction. So that is why you only move is represented. You may tell, sir, what is this? These instruction I have not written, but it is showing. So this is nothing but gen code. After this instruction, I have not written any code, but memory is what? Always filled with some data, either zeros or FF or some value. So whatever empty values are there, 0, 0. So which is represents some meaning or some instruction in assembly language, so it is automatically it is showing the disassembler. It is just showing that. So this is called disassembly. Disassembly means in assembly I write instruction using mnemonics. Disassembly is the opposite of that. So that we write the instruction and equivalent the binary values or machine language format. Now look at the move instruction now. Now this move instruction, whatever you're seeing here, this instruction has taken certain amount of memory. How much of memory? We will analyze this one. Let us take the first address, memory address, where the move instruction is stored. So it is the contents of that will be represented by this data. So move R0 #0x000A. Because why? I have written 10. 10 is what? 0A. So that means that this number will be stored in R0 after the execution of move instruction. What does assembler will do? Assembler will read this instruction move, will understand the meaning of this instruction and convert into machine language. What is the machine language? It is the ones and zeros. So now to represent ones and zeros, correct now, we do not have space. That is why generally hexadecimal equivalent of ones and zeros, that is binary, will be used. Both are same. If you just expand every digit by 4 bits, the corresponding 4 binary bits, it is nothing but a binary language only, ones and zeros. So whether I write ones and zeros, whether I write hexadecimal equivalent of ones and zeros, both is called as a machine language only. Generally, interchangeably, we use it. Sometimes we use ones and zeros, there is a space is there. Sometimes we use hexadecimal equivalent of that. Both the same. If I use a binary language, you should always remember that it is nothing but ones and zeros. To make it concise, easy to represent, we represent by hexadecimal equivalent. Why hexadecimal, not some other representation? Because in hexadecimal, for example, a digit 0 to F completely represents all combinations. For example, to start with is what? So it is 0, 0, 0. Next number is what? 0, 0, 1. It continues like that. So then 1, 0, 1, 0, that is A. Then after that, I have 1, 0, 1, 1. So if I goes like this, so the first one, second one. So for a moment, I'll go back, discuss that and come back here. So what I'm discussing now, how representation. So representation of hex numbers. So now, so the first number is 0, 0. The second number is 0, 0, 1. Next you have 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, then 0, 1, 1, 1, then 1, 0, 0, 1, 0, 1, then 1, 0, 1, 0, then 1, 0, 1, 1, then have 1, 1, 0, 0, 1, 1, 0, 1, and 1, 1, 1, 1. So equivalent of that is what? This is 0. So then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D. So I have one more left here. That is 1, 1, 1, 0. So E and then F. So look at here for a moment. That means that I have used all combination of bit pattern for the 4-bit number. So when I say 4-bit, how many combinations are there? So that is 2 to the power of 2. So 2, so power of 4, that is equal into 16. 16 combinations are there. Combinations are there. So all 16 combinations are represented by one digit, that is 0 to F. That means that, so to represent the 4 bits completely, decimal number system was not possible because it stops here. Hexadecimal is not possible, it stops at 7. Only octal is not possible because it stops at 7. Decimal stops at 9. Only hexadecimal can go up to F and represent every combination. So that means that now onwards, if I write E, my mind should say that it's 110. If I say A, 1010, both are same. I could have written in 1010 only as a concise representation. So now onwards, if I say binary or hex, you should always think that it is nothing but binary in machine language. So only for concise representation, we use hex. So don't distinguish between a hex and binary. Both are same. I can use sometimes AA, sometimes I can use 1010 or 1010. Depends upon the space and the understanding. I can use any one of the representation. So that is why you should see that when you write a program, if some hex codes are there, you should think that it's a binary. It is nothing but, there is no separate representation hex. It's nothing but binary and machine language. So machine language is represented either by binary representation or by hexadecimal, both interchangeably same. So by practice, you should be able to write any of the hex digit into its equivalent binary. Or if I give any binary pattern, you should be able to represent that in a hex digit. This is a compulsory in ALP program. If you don't mug this table, it is very difficult to develop assembly programs or answer the quiz perfectly. So I expect every one of you next 5-10 minutes, make sure that write this table in your things. Right on right side this representation 0 to F and see that can you able to do it. Take 3 minutes time, 2 to 3 minutes time. Take some paper. First write all the combinations, then write the hex digits. See that. Can you mug it up? If I say C, close your eyes and say that it's 110. If I say F, you should be able to see that. See that? Try to mug it. Or I'll wait for your response. If many of you say yes, I'll proceed to the next topic.
Yes, sir.
Only one I heard.
Yes, sir.
Two,
Yes, sir.
4,
Yes, sir.
5.
Yes, sir.
Yeah, okay. So I'm just taking some time to make you understand the basics because I'm not sure to what extent you understood in third semester. So that's why I want to take time and put all probably in the text file and just put it so that at the end of the session, probably another 30 minutes, you will appreciate these basics. Okay. Now coming back to here. So I was telling you that these machine codes, whatever we discussed, will be used to represent the instructions in the memory. So I was discussing about the disassembling, that is opposite of assembly. So what is disassembly? Knowing, identifying the binary codes or hex representation, as I said, of every instruction. So if I give you one instruction, I'll ask you what is the binary code of this instruction as per the ARM rules, ARM code design. You should be able to tell the using assembler and disassembler. So now if I say what is the machine language equivalent of MOV 010, I go to the disassembly window, I look at this instruction, and the left side they will indicate what is the address and what is the machine language equivalent of that instruction. So what is the first address? 0. Then there is no 1 is there is no 2 is there is no 3. Directly they will indicate a 4. That means that so 0, 1, 2, 3, 4 memory locations are required to represent the first instruction. That is the meaning of it. From the 4, again 4, 5, 6, 7. Next 4 bytes are required for the next instruction. Like that it continues. Now 0, 1, 2, 3. That means that 3 memory locations are required to represent move instruction. But now I have to know that exactly what is the contents of every location. Now I'll copy this data. What is the data? E3, A0, and then E3, A0, 00, 0A. So I'll go to the next screen. So I want to just see that what is the machine language equivalent of move instruction. Move, whatever the R0 I've used, comma, #10. So what was there? E3, A0, 00, 0A. Now tell me, this is what representation? This is hexadecimal representation. It is nothing but binary. If you expand every digit from your practice, now whatever you've done, you can write, if I ask you to write the binary equivalent of it, you can write like that. So 1, 1, 0, 0, 0, 1, 1. So A means 1, 0, 1, 0. Then 4 zeros are there. First 0, 0, 0, 0, 0. Second 0, 0, 0, 0, 0. Third 0, 0, 0, 0, 0. And the fourth 0, 0, 0, 0, 0. And the A, 1010. So this is the machine language equivalent of move R0 #10. Assembler has shown me using the disassembly window the given. This is what assembler does. What does assembler program will do? We'll take every instruction what you provide in a program, convert this into this number. This is what the assembler will do. What the compiler will do it? Compiler also will do it, same thing. But instead of move, it writes, for example, A plus B, like that, whatever the high level language you write, take every statement, converts into this machine language. But the only difference is, in assembly language, every instruction will convert into one binary pattern. That means that one instruction, that means that this is represented as a single instruction. Whereas in a high level language, when I write, say, so integer is equal to A plus B, if I declare a statement like in a C language, integer A equals some B plus C, if I write it, that means that this is not one instruction. This is converted into set of instructions like move, add, and everything. Then they further convert into machine language. So there's the only difference. In case of an assembly, there's a one-to-one correspondence between every instruction, every binary pattern. That means that no other binary pattern is possible for this instruction, irrespective of whichever assembler you use it, whether Kyle or some other ARM assembler or some other company's assembler. This is standard for given ARM core. That is for given architecture which you are used to develop your program. For that mean that ARM7, whatever the core I've used, you cannot have any other pattern other than this one. So this is one-to-one correspondence is there. Whereas if I write a statement like this using a C compiler and convert this into machine language, this will be converted into what? Set of move and add instructions. That set of move and add instructions converted for this statement can be many. That depends upon how you have developed a compiler, how optimization you have taken into consideration in a compiler. It can be 3 instruction, 4 or 5 or 4 only or 6, depends upon the how you developed your program. You may optimize it and use a minimum number of instructions. Somebody has not optimized this, so you would have used more number of instructions. Once you convert that into an assembly instructions, then again converting to the binary is the same like an assembler. So what does high level language do? High level language first converts the high level language statement into set of assembly language statements or assembly instructions, or you can call as a instructions of that architecture, and then you convert those instructions into machine language format like this. So this is the meaning you should be able to understand. So what is the meaning it carries? In case of machine language, one-to-one correspondence between your instructions and binary language equivalent. In case of a high-level language, one-to-one correspondence will not be there. It happens at 2 levels. First level, convert into high-level language into set of instructions, so which is depends on the compiler, and then after that, those instructions to machine language will be second step. So having understood that, so we will move to the next step. So I have now has a binary equivalent of this. Yeah.
Sir, I have a doubt.
Continue.
Yeah, so I read about something called LLVM, like a low-level virtual machine. So with that, it said that it like if you use CLang, you can compile it to bytecode and then use LLVM to execute. So is the bytecode like assembly code, or is it different from that?
Bytecode is nothing but a machine language. Bytecode is anyway machine language. But anyway, I'll just discuss this at the end of the session. Because whatever the virtual your statement, I'm not heard of it. But anyway, when I say bytecode, it should be the machine language. Anyway, we will discuss again. You can remember me at the end of the session after recording.
Okay, sir.
I have now converted this into binary language. Now we will understand the memory organization. So now how many addresses are there? So as we studied, there are 4 addresses for that. First address is what? 06000. Then I'll give just one gap after 4 digits, just to differentiate. So second address is what? 0x000, and then 001, 0x00, then 0010, 0x000011. So that means that, so this is equivalent to first address, that is 0th address. So the second one is a memory address 1. The third is memory address 2. The fourth is third, because I started from a 0. So what is this? This is nothing but memory address. So this is the memory address. Now, every address contains the data. So this is an address. So data. So what is the data? What is the size of the data? We know that. So there are 8 bits to represent the data. So one is D7, then you have a D6, and then you have 5, 4, 3, 2, 1, and then the D0. I'll write it. So every memory address you can store 8-bit data, because why? All the memories are organized as a bytes. It's a byte organized memory. So the microcontrollers or the processor, how they do an interface, they get connected to the ARM core or any other core, for example, even Intel processors. So the memory is always organized as a bytes. So every address represents 1 byte. If somebody says, your laptop, what is the memory? If I say 4 GB, I use the word B, GB. B means what? 4 gigabytes. So that means that 4 giga addresses are there. Each address represents 1 byte. If I say my mobile has a 2 MB memory, what does it mean? That 2 M bytes. So 2 mega addresses are there. Every address represents 1 byte, 8 bits. So this is a fundamental understanding. Now, since I know that this instruction occupies 4 bytes, also we studied in the architecture, ARM7, every instruction will always take the same size, that is 32 bits. That is divided by 8 means 4 bytes. So that is why 4 addresses I have written it. So in these 4 addresses, the complete instruction, 32-bit binary equivalent of this instruction is represented. How is it represented? We will see that. So first 8 bits, I'll take it. So this is the first 8 bits. So 1100, then 0011. So this is 1110. This is nothing but E. Then 0011. This is a 3. So the first 8 bits here. Now I look at the last 8 bits. So this is the last 8 bits. So 0 means 0000. Then A means 1010. So that means that 2 digits of your hexadecimal representation represent 1 8-bit number, or whenever your number is represented in hexadecimal, 2 digits will represent 1 8-bit number. So every 2 digits you can represent in 1 memory location. 3 digits, no, I cannot represent 1 memory location. Require more than 1 location or 1 byte. So always that 2 digits is a grouping we do it, because 2 digits represent 8-bit number. There's a fundamental unit to represent in a memory. So now you have E3A000A is a machine code for this instruction. Now, how do I store? Can I start storing 0001010, that is 0A in the first location, or can I start storing E3 in the first location? So you have studied that in the last semester. There is 2 ways you can represent the machine codes in the memory. Either you can start from lower 8 bits, or you can start with the upper 8 bits. It's called as, somebody can tell?
Little Indian and Big Indian.
Yeah, little Indian and the Big Indian. Now look at the disassembly screen and tell me which is the format they have followed. So if you are still not clear here, because sir, it is a given list digits, they have not clearly shown first location contains either E3 or 0E. So now it's my responsibility to show you how it is there in the memory. So I'll go to the one more concept I'm showing in the assemblers. So go to the view window. go to the memory windows. These are the windows that when you can open only at the runtime. So for example, when can you show the memory contents? Only when you are running. When you in the debug mode, at that time you are running. At the runtime only I can see the memory contents. So no, if you're not running the program still is not loaded into memory. So you cannot see that window. So some of the windows will come into picture. The moment you run, you can open those windows. So I'll say memory 1. It has not come. Again, I'll press it one more time. Memory window. So I'll press. Now this is the memory window. She that. Can you see the memory window on the lower bottom side? Can you see that?
Yes.
Hello.
Yes.
Can you see that? Yeah. Okay. Now, what is the address? 0800. Memory window provides an option to enter the address which you want to observe it. Since it's showing 400, I am not interested in the 400. 40 I'll tell you later what is the meaning of that. So now I'll go to 00 because I'm the first address 000000. So that is nothing but I am indicating here 32 bits 0. Instead of writing 32 bits 000, I am writing in hex equivalent. Every 4 bits 1 digit. So that is why 8 digits I've indicated. Now I'll say enter after that. The moment I say enter here, what is there in the memory? So which memory? The memory address 00 and the contents are stored here. So how it shows? Memory window always shows byte wise because every address represents 1 byte. So look at the first address. The first address, what is the content? 0A. Second address, that is 01. What is the content? 00. Third address, what is the content? A0. Fourth address, what is the content? E3. After that, there is no program was there, so that all empty space is available here. Because we have written only one instruction program. Now, I will represent, take that. The first address what? 0A. So I'll write here. 0A. 0A means, so it is nothing but, so 0, 0, 0, 0, 1, 0, 1, 0. That is nothing but 0A. So this is what is the first one. Similarly, if I write the second location, contents is what? 0, 0. So third contents is again 0, 0. Sorry, A0. So A0 means A0. So this is nothing but 1, 0, 1, 0 and 0, 0, 0. So this is A0. Then I have E3. So E3 is so 1, 1, 1, 1, 0, then 0, 0. So I have written E3. So now I have represented what is the contents in the memory location, both in the binary and also equivalent hexadecimal. Actually, in the memory, it is stored like this. It is stored like this. But so since it is not a concise representation, it's difficult for you to comprehend. So they generally show like this. But you should understand it is nothing but 8 bits are there in that memory location. It is nothing but this one. They are shown in this concise representation. So this is the contents. So 0A, 00, A0, E3. Now tell me whether what is the representation. You are referring to two types of representation. No? What is the one?
So this is a little endian assignment because the lowest bits are coming in the first, are occupying the first memory location.
Okay. Any other contradictory answer? Okay. You just verify once. It is a little Indian or big Indian. So we go with one of your friends said it's a little Indian. So first, if there are 32-bit number are there, the lower 8 bits first will be represented in the lower address. The higher 8-bit number will be represented in the higher address. You should know that 0, 1, 2, 3, which is the lower address? 0. Which is the higher address? 3. So lower portion of the 32-bit number is in the lower address. Higher portion of the 32-bit number in the higher address. As she said, little Indian. Okay, let's go with that. If any contradictions there, please raise your whether little Indian or big Indian like that. Okay. So now coming back to the program. So we have understood that the whole of this program size is 4 bytes. This is what you have to understand. So now if I stop this execution, and go to this statement, you can just look at this statement. What is there below? The program size is code is 4, read only, that is the data is 0, read write data is 0, so zi data is 0. We will understand other things little later. So now look at this, code is 4. So why code is 4? Because you had only one instruction. That instruction takes a 4 bytes. What are the 4 bytes? We have understood this one. So even though I written 4 statements, all the statements are not converted into machine language. Only the move instruction is converted into machine language. So that is the meaning of assembler directives and assembler instructions. This is how you can find out the size of your program. And also, once you know the size of the program, what is the contents of memory location also you can find out, which is generally not possible in a high level language. Even if it is possible using an Xcode, you can dump on a debugger, you can see that, but you cannot correlate that. But here you can very clearly correlate, oh, first 4 bytes. This is nothing but represent the move instruction, because in the disassembly screen, you can see one-to-one match between what you have written and what is the machine language. Whereas in a high level language, when you write a program, you may get a code size. Looking at a file, you can just dump the contents of binary language and some debugger or some screen notepad, but there is no one-to-one correspondence there. For example, integer c is equal to a plus b, that corresponds to how many instructions? You cannot find out unless you have to see the assembly output, and that you should know the instruction, you should understand. So when you write in a very low language, your output, machine language, and what you write, there's a one-to-one understanding is there. You can able to pinpoint the program at any one point, stop it. You can identify why it's not working. You can debug it. There is no way you can sort it out. You can program. You can 100% troubleshoot your program, because why? At the very low level, you can able to identify and able to see that what is happening in the there. So if any questions are there, we will go with the questions. Otherwise, we will continue with the discussion. Just look at the whatever we discussed for a moment. Okay, so now we have understood that what is an ALP program consists of assembler directives and ARM instructions. Then we have understood that so binary language and hexadecimal representation both are same. It's a concise way of representation. So what are the equivalents? We have understood that. Then we have understood one instruction, how it's converted, and how many memory bytes are required, how many addresses are required, how it's represented inside. So now onwards, any moment of time in a program, you can always go to the disassembly screen, see that how that instructions is going to work. Now we will understand some programs, how to work on those programs, and what is the meaning of those programs. Now, so before we will go that, I'll just complete one more concept called the memory used for your program. Now, as we go to the device, as I said, LPC 2148. So if you look at the device and how much of memory it has got, 512 kilobyte of on-chip flash RAM. That is, program memory is 512 kilobyte. That is a flash chip. It's nothing but read-only memory where your program is stored. Once you store, you cannot modify this data during the runtime. And then you have what is called as RAM, so which is 32 kilobytes of RAM, whose contents can be changed during the runtime. This is where you can store your variables. So these are the two types of memories is there. RAM 32 kilobyte and 512 kilobyte is your memory. Now, as I was telling you, just share other screen. So okay, this you study actually in Unit 4, but to get the clarity, so I want to introduce. Now, this is a memory map. I said this is the total memory supported by your ARM core. So, how much of memory, total memory, can be supported with ARM core depends on address bus. Since ARM core, that is whatever the ARM core, this is the your chip, ARM core chip. This is your ARM7 today my core. So this access this memory, whatever you have, 512K, through a bus. Look at this bus. The size of this bus is 32-bit. Since it's a 32-bit, that is 2 to the power of 32, 4 GB. So 4 GB is the total space what you have. So for your storing your program data or whatever it may be. Now this 4 GB is used to store, to represent or to hold both the program memory, that is 512 kilobytes, and also 32 kilobytes of SRAM. Now total my memory is what? 4 GB. But in that, the chip do not provide the complete memory. So if you look at this chip, whatever we are discussing, 2148 yesterday, this is what is present inside the chip. In this, you look at that, how much you have? 32 kilobyte of SRAM. I have the 32 kilobyte of SRAM I have. So, and then I have 512 kilobyte of flash. So only this is the memory. If you look at the whole chip, this is the only memory I have it. So that means that even though there is 4 GB support is there from 0 to 4 GB, the memory present inside the chip is only 512 kilobytes of flash memory, 32 kilobytes of SRAM. So where do they put it? It is decided by a lot of concepts. Number one, the flash memory is put in the beginning because after reset, microcontroller or ARM core expects your first instruction to be in the first address, that is 0000. We have seen that in assembly. Whenever you start debug, it always the program counter points to 000. So that is why the manufacturer will put 512 kilobyte in the lower portion, that is which align to 0000. So this is where it starts, 512 kilobyte. So that means that 00 to 512 kilobyte is the range of memory for this chip what we are using. So now I'm going to here. Now I'll go to the target. So look at the target. In the target, they have given the memory areas. So read-write memory areas for the program memory, read-write memory areas for the SRAM. So now they have provided the program memory, that is 512 kilobytes. It's a ROM. It's a ROM. So what is the range of that? 512 kilobytes is what? 0x800000. That means that what is the size? It starts from 00. The size is what? So whatever the range, it is provided here. That is 512 kilobytes. So the starting address is what? This one. It is provided this much of memory, whatever you are seeing here. So 8 followed by, so 4 zeros. You calculated. It should represent 512 kilobytes. 512 kilobytes. They have given the size in hexadecimal. You can always go to the calculator. So this is a very useful tool to convert hexadecimal into decimal. So now I've just taken a calculator. So I'll go to scientific or programming mode. So let's say the scientific, go to the programming mode. So you get a representation, hex, decimal, everything. So I'll go to the hex. So type 8 followed by 4 zeros. 1, 2, 3, 4. Then I'll convert into decimal. So how much you got? 524.28. Because 1 kilobyte is what? Divided by 1 kilobyte is 1024. So divide this by 1024. So how much you get? 512. So that means that, so this is the range of addresses and this is the capacity. So whenever you select the chip and start developing a program, automatically in the target, it shows that what is the first address and what is the last address. What last address is nothing but what? First address plus this value is the last address. So this is nothing but a size. So you should always know that what is your total program capability, what is the range of addresses. So that is what in this figure it is being. So we have represented. So 512 kilobyte is the addresses. Am I audible?
Yes.
Yeah. So this is the addresses. This is how you should be able to understand that one. So now this one. This is about the program memory. So
I have a doubt. What are the other options that are present? There's round 1, round 2, round 3. What is all that for?
now can you just repeat your question?
Yes, sir. So only out of all of these boxes, there is like only one which is filled, right? What are the other ones for? There's round
Round 1,
round
round 2 like that?
Yeah.
So this is not there. For this chip, you are not placed like this. If at all, if you have added some extra memory outside or something, any option is there, you have to indicate that. You have to indicate that what is the range you are providing. So there's a facility, maybe that you can just verify. So these are the facility where you can able to specify the memory if anything is different. By default, this is for this chip, this is the memory. So you can able to indicate. Now the startup is what? This is a startup code. So this window is a facility where you can able to indicate the address range, that is a mapping of other memory chips which you have added to the board. Say for example, you want to design something on a board which you added some extra memory which is not there provided by the microcontroller. There is a facility so that in the assembler or that is in the development environment, you can indicate what is the range of memories are there in your board and which is the startup. So this is what is called customization is there for the boards of your choice, whatever you have developed.
Okay.
So for this is by default. This is taken because for 2148, this is a default size they are provided by the microcontroller. I have not added anything extra for that. Similarly, now when I come to the RAM area, SRAM area, so internal RAM 1 is nothing but which is already provided. The manufacturer is what? 0x4000 it's provided, and then 08000. What is the 400? So we use this extensively in the assembly programs later onwards to store our data. When I add 10 numbers, where do I store my answer? I should store in the RAM only. So at that time, I should know that there is a RAM. So now look at this memory map. The 2148 chip manufacturers have implemented the RAM, 32 kilobyte of RAM, at what location? From the 1 GB onwards. From where? From 1 GB onwards. This is what? This is 0 GB. 0 GB, if you continue, it goes to what? 1 GB. What is an address of a memory location where 1 GB starts? That is the address, whatever you are seeing here. So 0x4000, if I copy it and paste this in a calculator. So I'll go to the hex mode. I'll go to the hex mode and type this one. This is 0x400. I'll convert into decimal. You can always see that in decimal. So this is decimal is what? So 1 GB. You can divide that by again 1024. So that is this one. Again, you can divide it by another 1024. So this is 1 GB, 1024 kilo into kilo. That is, so this is the 1 GB. That is 1 GB means what? So 1024 again into 1024 kilobytes. That is a 1 GB. So whatever the memory indicated here, it represents what? 1 GB. So it is matching with my memory map also. So at the 1 GB they allocated. You may ask the question, Why at 1 GB they are provided? They could have provided in there. It's a decision of the manufacturer of the chip. They will allocate spaces for the different peripherals inside. Space, they will allocate the addresses for the RAM. They will allocate the address for the flash. Everything they will take a decision when they manufacture. But once the manufacture, and start using, you cannot manipulate these one. These addresses are fixed for a given microcontroller chip. So now coming back here, so this means that 1 GB is the place where 32 kilobytes starts. How much? 8,000. So if I copy 8,000, and put it in the calculator. So if I go to hex and paste that, so this is 8,000, convert into decimal, how much you'll get? 32 kilobytes. So 32,768 means what? Is a 32 kilobytes. So this 32 kilobytes is the space what has been indicated. This is in the device. If you look at that, what is the size? You can see that how much is the memory, RAM they provided, 32 kilobytes of RAM. So that means that you can just say that now onwards. So this chip, whatever you're going to use for developing LPC2148, has got 512 kilobyte and a memory range from 0 to this address, and it has got a 32 kilobytes starting from 0x400, that is 1 GB, up to 32 kilobytes. So now I have understood that how memory is organized. Why I require this understanding is means when I store my answer, in the program, I should be able to look at in the memory window where is my answer is stored. So where we store it at 0x4000 onwards. That's what you type in the memory window when you look at your answer. So this completes another discussion about the memory, the map. So you have to understand that. So before start writing a program, you should understand that memory map of the chip. So memory map of the controller you are using. In this case, it is LPC2148. That is ARM7 based architecture I've used NXP here. The RAM, that is the flash memory, that is flash RAM. It is used up to what? 512 kilobyte starting from 0. So then it has got from 0x. So 8 followed by 4 zeros. So this is size, this plus this totally. So then it has got SRAM. So which has got SRAM capability was that 32 kilobytes was there, 32 kilobytes. So it is starting from 0 to 0 plus 0x 8,000. So 8,000. So this is the range of memory. So this is the area I should be able to remember that where it is stored. So this is starting from where? Not 00. Sorry, this is starting from 0x40040. So this is an address where it's starting from here to 4002. So whatever the value, whatever there, that is 0x4000 plus this value, whatever their value, So this is the range of addresses. So here what is address? 0 plus this one. This is the range of addresses. First address and the last address. Last address should be what? Maybe 8,000 minus 1 you have to say. So you have to say, so minus 1, the last address, because you're starting from a 0. So here also what? You have to say minus 1. So these are range of addresses for this chip. We have understood that. Now we will go back here. Now we will try with few programs. Now I'll stop sharing this. I'll go back again. I'll share now. This window. So now look at this screen for a moment. Now we will use a few instructions to understand how the instructions are developed. Now all the instructions, whatever you have, so inside the ARM, those instructions are classified into all the instructions into, so broadly into following types. So what are the types? The first instruction is called data manipulation instruction. Data manipulation instructions. So these data manipulation instructions means what? The data transfer, it contains like a move instruction, whatever we have used. It's move instruction. It contains arithmetic instructions. So like whatever we have used, the add instruction, this is arithmetic instruction. It contains the logical instructions. It is like, so we'll be using later. It's called as, let's say, AND instruction. So you have and instructions like that. Then you have, so these are the instructions, what will be generally present. Then you have also shift and rotate instructions that already I used in the morning, the class. That is, so we use like an LSL, logical shift left, rotate, and other things like that. So these are the data manipulation instructions. We have one set of instructions. Second is called as a branch instructions. BRNCH, branch instructions. So these are the instructions I can branch at loop. What are the instructions? We know that example is one instruction B. We have used that. So branch and loop to the same logic. We have used it. So in every program, you're supposed to use that one. For example, in the example I've used here, that is stop B. So I'll just copy this instruction and put it in the example program. So always this instruction is required. We generally put this one here so that it will be looping at this place, not allow the program to flow from this location. So this is a branch instruction. So there's another last instruction called as, that is, I said most of the instructions use the registers to have that operands, except there are certain instructions there which are used to fetch the data from memory or store the data into memory. Except those two instructions, all other instructions are what? Use registers as operand. That is why it's called as a load and store architecture. So the third type of instruction called load and store instructions. Load and store instructions. So these are the only instructions available to access the memory. If you want to fetch something from memory or put something in memory, what are the instructions you would use? Only load and store. So no other instruction can access the memory. So all these instructions, whatever we have discussed here, they only access what? Registers. Only this is called as a load and store instructions. Now we have to study in the next probably 1 or 2 weeks about all the instructions what are supported under the data manipulation, under the branch, under the load and store instructions. Since we will start developing a program, not we're developing a program before completing all the instructions, I'll be combinedly using some of the instructions in each of the groups. So I'll explain what is the meaning of that whenever required. So, but parallelly we'll be learning about the instructions in detail as well in the theory also. Now, so now coming back to the program. Now, after knowing that all the instructions are of 3 types, now I want to start implementing a simple logic. So what is my first programming assignment now? My first programming assignment is now, I will be implementing an equation, that is an equation like an expression which includes, which indicates, which expression which contains the variables. Now, so let's see that what is that expression. Now, my first programming now is what? So write a program to implement following expression. This is my, so what is the expression? This is my expression. 2 into a, correct one. That is, this is my expression. I want to implement in a assembly language this one. In a high level language, what we do? We declare one variable for a, we declare one variable for the b, then we use an operators, then we write print. The sum I store in 2 into a plus b, and store it. That means that. So in very simple way, I can say integer a comma b. So answer. So in high level language, I can say what? Answer equals. So 2 into a can be capital also, plus the b. That's all. Then I'll print my answer. This is how we represent in a high level language. Now I don't want in a high level language, I have to write in assembly language. So when we write it, is it audible? Hello? Is it audible?
Yes, sir.
Yeah. So now I'm able to show this in a assembly language. So what do I do it? So my programming logic starts that. In assembly language, how do you represent variables? That's the first question. You should be able to answer it. As I said, there are only 2 places where you can store your data. There's only 2 places inside that. So what are those 2 places? One is inside the core where you have the registers. It is very easily accessible and no extra time is required. So where is another place where you can be able to store your data? So the other place where you can store data is the memory, that is which is outside the core, where you know that there are 2 types of memory we have discussed now. One is a flash memory, other is called as a SRAM. So I can use SRAM because it's a which I want to modify during the programming stage. So there's only 2 places I can store my data. One is I can store my data in the registers, or I can store my data in where? In the SRAM, I can able to store it. So to start with, always a good program is what? First of all, see the possibility of using the registers. If there's no possibility of using the register for implementation of logic, then only you will move out of the core, access the memory, use those memory location to implement your logics. Since now in this case, now this expression is what? I have a two variables are there, A and B. So these variables I should able to represent, because variable is one which requires a memory location where the values can be changed. So I can represent these variables either by registers or by a memory location. Since the possibility of using registers is there, I'll use the registers now. Now you should take a decision. So what registers I'm supposed to use it? It is your decision. Let's say I'll randomly take R0 and R1. There is no hard and fast rules. It is a programmer option. It's a program, the flexibility for a programmer. So now I'll use move R0 as a one register. Then I'll use move R1 as a other register. So now you can assume any value because you are going to run the program. What is the value you are going to feed A and B? Either at the time of running the program, you should take a decision, or let A is equal to 2, let B is equal to 2. Or once you run the program, then you should know that register, go to the register, then you can type the value at the runtime. Then you can change the values. Or what you can do is, if the system is completely sophisticated, then you can able to feed through the keyboard. So always you have to remember that I am writing assembly language program. This code is executed on the platform that is in a microcontroller chip where I'm running it. Does the microcontroller chip has got any keyboard or mouse is connected? No. So that is why you should always think that. So generally in the printf, scanf like that, I cannot use it because why? You are running this code on the microcontroller chip. That is a chip is the only chip available there. Nothing is there. I've connected it. So always you should keep in mind where is you running your codes. What is a target environment? That you should keep in mind. Always is a big shift between the way you write a program in a high-level language, the way you write a program in a low-level language for a target environment. Since now only possibility is what? At the time of writing the program only, I'll assume. So A equals some value. Say let's say 5 I'll assume. So B is equal to let's say 2. I will assume that value. So then at the time of writing a program, since I make an assume, I say hash 5, then I'll say hash 2, and this is given it. Now I want to write a code for this now. What does that I have to do? I have to implement the logic. Now I have taken the R0 and R1 as representing A and B and assume certain values 5 and 2. Now what should I implement? I should include 2 into A. I should be able to implement it. How do you implement 2 into A? How do you implement 2 into A? So here I am introducing one concept here. Now, as I was telling you, when I explained the architecture, ARM has one logic called as one fundamental unit called as a barrel shifter. So which I demonstrated in theory class 2 in the morning also. The barrel shifter has a capability of shifting a number 32 bits, left or right in a single shot. So whenever you perform any arithmetic operation, it is always the possibility is there. You can able to shift the number and perform the arithmetic operation. This possibility is there in ARM. This is a very good feature of an ARM. That is, I can add, subtract, multiply, or shift, or whatever the logical operation. When I'm performing it, one of the operand I can make it go through the barrel shifter, perform certain operation called shift left or right or rotate, and then perform the operation. So we have to understand that what is the simplest way, what is the fastest way to multiply a number by 2? This is a standard quiz question asked when you are when you appear for a systems programming as a systems programmer. So what is the fastest way to multiply? So one is you can use a multiplier in it, but that is always multiplier is what? It takes certain time, more number of clock cycles compared to the basic ALU operation. So the fastest way to multiply a number is always by shifting the number. So when I shift the number left by 1 bit, say let's say that I have a number 0010 is a number, I have that. Now shift this number left by 1 bit, what do you get? So 0100, this is a number I get. What is the meaning of 0010? It is 2. If I shift the number by 1 bit, what it becomes? 4. So any number, if you shift it left by 1 bit, it's nothing but multiplication by 2. So this is the fastest way of multiplying a number. That is why whenever you have got a multiplication component is there in a expression evaluation or your program First see that can you use a shifting operation and perform that logic. If you're able to do that one, use that one. If not possible, then go for actual explicit multiplication instruction or repeated addition, whatever it may be. So then that is a better option. So this is the fastest way of multiplying. So because it takes what, only one clock cycle, it does not require again another operation. If I multiply, what will happen? First I have to multiply, then I have to perform addition. It's a 2 clock cycles. Of course, clock cycles for multiplication plus clock cycle for addition is required. If I perform in a single instruction addition plus multiplication with a shifting operand, then what will happen? Within 1 clock cycle I can finish. So like this, always you should think that when you write in a assembly language. That is architecture you should keep in mind when you implement. Now, since I perform both, and I'll do it, then R2 I'm able to do it. So after the R2, what I'll do it? So I want to multiply A into 2, that is R0. So I will add R1. So the second one, whichever that I'm adding, that is R0, is now most of the data manipulation instructions are 3 address format. This is a 3 address. Look at 3 address. How many operands are there? 3 operands I can represent. So you should understand that ARM7 supports 3 address instructions for data manipulation instruction. All instructions for data manipulation are what? 3 address format. That means that you can represent 3 operands in the instructions. So I have done R0 now. 3 operands are there. What is the meaning of that? R1 plus R0 is added and put into the R2. Now always the one operand, that is if there are 2 operands are there, the last operand you can always pass it through a barrel shifter. When you want to pass it through a barrel shifter, you should indicate after the R0 what is the meaning you want. So what is the meaning I want after this one? I should able to indicate what? R0. So I want left shift. The barrel shifter should left shift it, LSL. The moment after the R0, if you indicate the keywords like this, so LSL, so right shift, the rotate, there are certain options there. We will discuss that. If I use any of these operations, then what does it mean that? So I am invoking the barrel shifter to perform on this operand and then supply this operand to an ALU. So how much I have to shift? 1 I have to shift it. What is the meaning of this instruction? Take the R0, use the barrel shifter, shift it left by 1 so that it becomes what? So your R0 is nothing but what? 2 into A is performed. Then what? So add this result, that is the shifted number, shifted R0 into what? The plus R1. R1 is what? The B. Then store this answer into R2. That is nothing but your answer. This is answer of this expression. So now I performed it. What is an answer? You're supposed to get it. If I take 5, 5 into 2 is what? 10. So 10 plus B. B is what? 2. 12. So 12 is nothing but 10 is A, B, C. C is the answer. You're supposed to get it. So I'll stop the program here. I'll just compile the program. I'll compile the program. Now I'll see that whether I get the answer if I perform it. I'll keep watching the registers here. So execute it, perform that, the first instruction. So it has gone to the second, it's observing here. So sorry, I have not compiled the program. So I'll compile the program. It's very important you compile whenever you make changes, otherwise it runs the previous code. So it compiles the previous code. Whenever it shows an error, please go to that line, use a scroll bar, go to the screen, double click on the error. So now one error is a missing comma, just double click on that. So missing comma is there. So what is the statement I have missed? I have just missed R1 comma R0 LSL R2 or whatever the logic I've used there. So I will go back to my program, see that what is the logic I have to use it. So let's see, I have put a comma there. I'll compile. See that whether there's any error is there. Now there's error is removed. So whenever you make any mistake, on the bottom side you have to come, it shows the error. Use a scroll bar. You can move like this and click on the error line. Whatever the error you get it. If you just click on the error line, then it shows this one. For example, again I'll make a mistake. So again I'll compile the program. It shows the error. Look at that way it shows. It's an error is there. Use a scroll bar. Move like this. Keep my mouse where I'm doing it. So it shows the errors. Wherever the error is there, don't look at the warning. Error is there. Double click on that. If I double click on that, so you can see the indication here. So that means that So this is the line, there's an error is there. Then you should look at the format. Okay, so I require a comma here. So then again, compile that and see that there is no error is there. So this is how we should be able to look at it. Now I run that code. So execute the step by step. So 5, 2, you got it. Then I added these numbers. So then this is nothing but C, I got it. So C is nothing but the value represented by that expression. So understand this statement, whatever I done it. So now you got the answer. So if you add the flags here, that is yes, if you add an S here, then the flags also will change for this one after the addition, whatever the result. Now try this program, everyone on your screen, before I give the now another 2 expressions which you have to do on your own. Everyone try this program now. Try this program. Understand the meaning of all the instructions. What are the instructions you should be able to understand by this time? Move and add and LSL. Understand the instructions. Now I'll give another 2 statements for you to execute. Before that, you finish that, take another 5-6 minutes. I'll stop the recording so that we can have a discussion what is required, because whatever I explained till now, it's